In this example, we're going to do a one variance hypothesis test, and then we'll follow that with a one variance confidence interval. So one variance tests and confidence intervals are similar but yet much different than what we've seen with one mean or two mean hypothesis tests. We have to introduce a whole new distribution. We're no longer working with a z-table or a t-table. We have what's called a chi-square table. So chi-square is a Greek letter. It's like an X with a little 2 there. So chi-square, and it's kind of like a fancy X. That's a little bit better one. So you're going to see the letter chi, C-H-I. It's not chai, it's not chi, it's chi. So kind of like K-I, if you want to pronounce it that way. So in this example, let's look through it. With individual lines at its various windows, a post office finds that the standard deviation for normally distributed waiting times for customers on Friday afternoons is 7.2 minutes. The post office experiments with a single main waiting line and finds that for a random sample of 25 customers, the waiting times for customers have a standard deviation of 3.5 minutes. With a significance level of 5%, test the claim that a single line causes lower variation among waiting times, in other words, shorter waiting times for customers. So what I can tell from this problem is that there are some key words. Lower variation. We're not talking about the average time that someone spent in line. It's the variation among the waiting times. Variation among waiting times for the customers. And we're also given facts about the standard deviation. We know that they have found that with individual lines, the standard deviation is 7.2 minutes, but then we do a sample, collect data, and the standard deviation is 3.5 minutes. So there's no mention of an average at all. Sometimes the problem might throw in an average, but don't be misled. Look to the end and see what sort of test we want to do and then what parameter we're testing about. So now that I know this, that we're going to be testing about a standard deviation, I need to write my hypotheses to reflect that. So we have our null hypothesis, H0, and our alternative, HA, so just like before. And we need to use the correct parameter. Before we used mu because we were working with means, but now we're working with a standard deviation. So the null hypothesis is assuming the population standard deviation to be equal to a value, and that is 7.2. That's kind of like maybe some old information that we've assumed to be true. That goes in the null hypothesis, or maybe the gold standard, whatever the value is. And then the alternative is what we're trying to see if there's a change or a difference. So in our case, the old standard deviation was 7.2, and we're hoping with a single line that the standard deviation is going to be less, and it will be less than 7.2 minutes. Now remember, our sample found 3.5 minutes, so we're trying to figure out if that 3.5 is significantly less than 7.2. We can't just look at the difference and say, oh, it's 4 minutes, that sounds great. We need to do a hypothesis test to statistically determine if this is true. So one note is sometimes textbooks will write out these hypotheses a little different. Some will say sigma squared equals 7.2 squared. And then the alternative, sigma squared is less than 7.2 squared. So this hypothesis, these right here, this is actually stated in terms of a variance. Sigma squared is a variance. So the hypotheses get written in terms of variances. These right here that we did are written in terms of the standard deviation. One is not better than the other or worse than the other. It's just different preferences among textbook authors. One book that I look at always uses sigma squared. Our textbook, the Weiss textbook, uses sigma. In a way that can make more sense, because if you're testing about a standard deviation, let's go write the standard deviation and the hypotheses. So that kind of makes sense. All right, on to the next step, significance level. So we're told with a significance level of 5%, here we go, so we're going to use alpha equals 0.05. If this wasn't given to you in the problem, then you get to make it up yourself. You could choose 5, you could choose 10, or 1%, whatever you like. So the next step is our test statistic. Now, the variance, or the standard deviation here, has a different distribution. It follows a chi-square distribution. So our test statistic is going to look a lot different than what we've seen before. What statisticians have found is if you take the sample size minus 1, in other words, your degrees of freedom, and you multiply it by the standard deviation squared, and then divide that by sigma squared, what we get is a different shape of data, and that is called a chi-square distribution. So a chi-square distribution has a couple different properties than normal. That's supposed to be a straight line. First of all, it starts at 0. The normal model had a center of 0. So did the t-distribution. Everything was symmetric about 0. The chi-square distribution is really different. It has a starting point at 0. It goes up, kind of looks normal, but then it really skews to the right. So it will leap up high and then go down and just have this really long tail. What does happen though, the larger the sample size, the more normal that this curve is going to look. It won't ever be perfectly normal because it's cut off here at 0. And you can make sense of this 0 starting point as the minimum standard deviation. If you have data, the smallest standard deviation that you could ever have is 0. So our chi-square distribution starts at 0. There are some other funny shapes to this distribution, like if you have really low degrees of freedom, it starts way up high and then goes low. If you have a really high number of degrees of freedom, it will shift this way and go down. So this curve really changes shape depending on your degrees of freedom. Just like the t-distribution changed with degrees of freedom. But this one looks kind of even funnier because it really has this like reverse J shape to it, and then the right skewed off to the side. So our test statistic says if you take these numbers, multiply them, and divide them, you're going to get a chi-square shape. So we'll fill in what we know. From the problem, it said we took a sample of 25 customers. So that means 25 minus 1. And then we're going to multiply that by our sample standard deviation. So up here, it said from our sample, we had a standard deviation of 3.5. So we'll multiply by 3.5, and we're going to square that. So notice that we're squaring, that's just what the formula says, but the squared number, it can make sense to write the hypotheses with squared values because you're going to take the 7.2 squared and that's going to go in the denominator of your test statistic. So it can make sense to write your hypotheses with a squared because you're just going to take that number and put it on your denominator. So this is kind of like a ratio of the standard deviation from the sample compared to the standard deviation from the population or whatever we assume to be true, and then scale it by the sample size, well, degrees of freedom. So we do that math here, and we're going to get a chi-square value of 5.67. So round it out to 2 decimal places there. Our chi-square value is 5.67. Now you'll notice this is really different than the normal model. The normal model, you might be, -3 to +3. Chi-square values go from like 0 up into the 20s, the 30s, the 50s, just depending on your sample size. So you can't just look at this number and go, oh, I know the results of this test, because it's on a totally different scale than we're used to looking at. So let's now figure out what our critical values are, and then we'll also compute the p-value using StatCrunch. So our critical value was based on the significance level. We know that alpha was 0.05. The hypotheses up here, the alternative hypotheses, told me we were going to do a left tail test. So that means I need to have a left-sided critical value. So I'm going to sketch out my chi-square distribution, make sure it's kind of right skewed here. So with our left tail test, that means we're going to have a critical value over here on the left side. And then when we mark off this area right here on the left tail, which is totally not to scale, this area will be 0.05. So my goal is, what is this chi-square value that is going to put 0.05 area on that left side? So this is kind of similar to what we did in other hypothesis tests, but now what's different is the chi-square model. The tables in the back of the book don't work like the normal tables. So pay attention to this because we're going to see different numbers around our chi-square table. So before I go find this chi-square value, I want to point out one thing. If we have 0.05 area on the left tail, then what's the area over here on the whole other side of this chi-square distribution? Well, hopefully you said 0.95. 1 minus 0.05 says 0.95. So I'm actually going to change my chi-square value just a little bit. I'm going to add in a bit more information. Chi-square 0.95 equals, well, we're going to figure this out. So I did this because now when we go to our chi-square table, here's a little chi-square distribution. The chi-square table only looks at area on the right side of the distribution. Now that's totally opposite of the totally opposite of the z table. The z table took area to the left. Chi-square gives you area to the right. This picture right here, which is just one example, it's not to scale for every problem, but it says, hey, here's your area on the right side, and then this is going to be the chi-square value that puts that area to the right of it. So when I knew that my left area for the problem was 0.05, that meant 95% of the area was over to the right. So I have to look up along the top of the chi-square table and find the 0.95. This chi-square value puts 90% on the right. And here's the one that puts 95% on the right. And then it keeps going. 975, 99, 995. Those are often values like with a 1% test, with it's one-tailed or two-tailed. It gives you all those options for common levels of significance. So what I want here is chi-squared 0.95. And then on the left side is our degrees of freedom. So I would go down to 24 degrees of freedom. Let's see. So we have about 24 degrees of freedom. Well, that's not drawn very well. Let's try to do this again. 24 degrees of freedom. And I know that I need chi-square 0.95. So where the column and the row meet seems to be right here at 13.848. There we go. Sort of highlighted there. 13.848. That is the critical value for this hypothesis test. And remember, like I said, these chi-square numbers are much larger. Just take a glance at this table here. At the bottom, we have chi-square values that are in the 50s and 60s. Here's one that's up in the 80s. They're in the teens. They're in the 4s, the 5s. They're all over the place. And that's just the left-sided critical values. If I move one more page in the table, we'll come back to the hypothesis test in a second. If I go to this next page, now I have chi-square values that put 0.005 area in the right tail. So these are like small right tails. 1% in the right tail, 2.5%, 5%, 10%. These are kind of like the complements of the other table. It's the like the mirror image in a way. And then degrees of freedom down the side. So check out these chi-square values. We're in the 20s, the 30s, the 40s, 50s, and if we get a large enough sample size, we're up here in the hundreds for our value on that chi-square distribution. So I just wanted to point out that these numbers are just going to be larger than a normal distribution, and we don't really have that sense of how the test is going to conclude based on our test statistic. So I want to go back over here, and our critical value, 13.848. So chi-square 0.95 was 13.848. So back over here, we had 0. This number right here is 13.848. And if we land anywhere in that region between 0 and 13.848, we're going to end up rejecting our null hypothesis. So what did we get? 5.67. So that is, let's find a different color here. How about this yellow? So we're kind of right, I don't know, about there or so. That's where our critical value landed. So we landed in our rejection region. So chi-square equal to 5.67 is in the rejection region. All right, so that's our critical value. Let's look at the p-value, because that might be another way to do this. If you don't have a chi-square table around, you would maybe want to use the p-value method, or you could do all of this in StatCrunch. So we're going to come back and do the conclusion after we get the p-value. So let's set this up. I'm going to make this a little bit pinker right here. So this area, this tiny pink area, that's going to be our p-value. Let's use StatCrunch to compute that p-value. So p is going to be equal to something. Let's figure it out. All right, so let's go to StatCrunch. To do this hypothesis test in StatCrunch, I'm going to do the entire test. So we'll go to Stat, and then down in the menu here, we want Variance Stats, and we're going to use one sample because we just took one sample of 25 people, and we have the summary of the data. We don't actually have the numbers from our 25 people, but we just have the summary of the results. So we'll click on this. Our sample variance. So what did we get from that? We had a sample variance. So I'm going to need to do a little bit of math here because I need to know what the sample variance is. I know the sample standard deviation, but not the variance. So let's see, we have 3.5 times 3.5 is 12.25. The sample size was 25. And we're going to do a hypothesis test for sigma squared. So yeah, that looks a little different than the hypothesis that we did earlier, but all we have to do is square that sigma. So remember in our null hypotheses, we had 7.2. So I need to square that. 7.2 is the standard deviation. Multiply it by itself, and we get the variance. We get 51.84. And then that number pops up down there. Change the hypotheses, so it's the alternative, it's the left tail test. When you do a confidence interval, you just change the button there. That'll be pretty easy later on. So we have our variances. Remember, pay attention to the words. Choose the right alternative hypotheses, and then push compute. All right, so here's our little box of results. We have a test for one population, well, variance, but that's a standard deviation if we square root it. Here are our hypotheses, sample variance, the degrees of freedom, the chi-square test statistic, 5.67, yep, that's what we got. And our p-value, it says it's 0.0001, so it's actually very small. There is a way to compute the p-value a different way, and it's just the p-value. It's not running through the entire test. At this point, I could go back to my paper and write down the p-value and I'd be good. But I want to show you this extra side thing. Stat calculators, you're probably familiar with this. Go down to chi-square. If I tell this calculator my degrees of freedom, 24, and I want to find the probability that I am less than, what was it, 5.67, 0.67, that was my test statistic, and push compute, I will get a picture of the the chi-square distribution, and then it's going to shade the area of my p-value. Well, funny enough, my p-value is so tiny, 0.00004204, so it's so tiny that you can't even see it down over here in this lower left. Remember, our test statistic was 5? Well, that's like right there. It's kind of almost off the charts. So there's really nothing to shade, but it is over there. We can see that we have a tiny p-value. If we had a bigger p-value, it'd be maybe a little more valuable because you could see the red that would be shaded over here on that left side. So just another way to compute the p-value without the entire hypothesis test. So I'm going to close out of that. I'll go ahead and just use this p-value. I could write down all those decimals, but 4 decimal places for a p-value is a pretty good number. So back over here, the p-value, I'm going to change my symbol now that I know just how tiny it is. P-value is less than 0.0001. And we know that when the p-value is low, h0 must go. So our conclusion, both ways, was reject h0. So the p-value was less than 0.05. That's why we rejected the null hypothesis. So reject h0. So what was our original question? Well, we know we're rejecting something. Does a single line cause lower variation? Yeah, we rejected a standard deviation of 7.2 and we're supporting an alternative variation of less than 7.2. So we could say there is enough evidence to support a standard deviation less than 7.2 minutes. The single line will have customers waiting times vary less than 7.2 minutes. So in my next video, we'll look at the same example, but this time we will do a confidence interval for the standard deviation instead of a hypothesis test.